welcome to Two Projects. In this video, we are going to explain about the project that is Smart City Traffic Management, that is acoustic based vehicle detection using stacking based ensemble deep learning approach. Before getting into the execution, first let us understand what is the project about. In daily life, we all have experienced the frustration of being stuck in the traffic, especially when you hear the sirens of an ambulance or fire truck trying to make it a way through. These vehicles are lifelines, getting people the medical care or the emergency response they need in critical moments. But the reality is, traffic congestion often delays their passage. And those precious seconds or minutes can make all the difference. Unfortunately, National Crime Records Bureau estimates that 24,012 people lose their lives daily due to improperly delayed medical care, largely because emergency vehicles can't get through in time. So this is where acoustic based emergency vehicle detection systems comes into the play. These systems works by recognizing the distinct sounds of sirens and classifying them accurately, allowing traffic systems to react faster. Think about how much smoother and quicker emergency vehicles could travel through cities if we had a system in place to detect them before they even reach the traffic. By integrating this technology into smart city infrastructure, we could cut down the time it takes for ambulances and fire trucks to navigate through traffic, saving lives and reducing congestion. In essence, this solution could make cities safer and also more responsive, ensuring that help arrives when it is needed the most. So, in the past, there have been attempts to use sound analysis to identify different types of vehicles, including emergency ones, but these systems often fall short in real world situations. The main issue is that they don't always work accurately or adapt well to the unpredictability of actual traffic conditions. For example, background noise like traffic or construction sounds can easily interfere with the system's ability to correctly identify an emergency vehicle. And here, the real challenge here is to build a system that can quickly and reliably detect emergency vehicles in real time, even in busy urban areas. This is crucial because in an emergency, every second counts. The goal of this project is to improve upon existing systems by using advanced acoustic based detection, that is, acoustic analysis and machine learning techniques. By doing so, we can create a system that not only detects these vehicles accurately but also ensures they get the priority they need on the road. This will ultimately make the traffic management more efficient and help save lives by reducing delays in emergency response times. So, this project proposes an advanced solution for detecting emergency vehicle sirens and road noises to improve the traffic management in smart cities. So, here the system uses the stacked ensemble deep learning approach, which combines multiple machine learning and deep learning models. So, here first we employ multi-layer perceptron, that is MLP, and deep neural networks as a base learners. These models are strong at identifying patterns in complex data, such as distinguishing between different types of sounds. And then LSTM, that is long short-term memory model, is used as a meta learner. This LSTM, it plays a crucial role by considering the temporal sequence of the sounds. This helps the system understand how sounds evolve over time. So the combination of multi-layer perceptron, DNN, and LSTM allows the system to detect emergency vehicle sirens with higher precision even in noisy environments and ensures that these vehicles are given priority in the traffic. Moving on to make the system more accurate in identifying emergency vehicle sirens, the project focuses on using advanced feature engineering techniques. This means the system takes the raw sound data and extracts important characteristics or features from it. These features include Mel frequency septal coefficients, that is MFCC, which capture the timbral qualities of the sound, root mean square error for measuring the energy, and spectral centroids, which helps to identify the brightness of the sound. And other features like spectral flux, Mel spectrogram, chroma contrast, and tones are also used. Each of these features provide a unique way to distinguish between different sounds, helping the system differentiate an ambulance siren from the regular traffic. So, by leveraging the strengths of each model, this approach optimizes overall performances and improve the emergency response times, ultimately contributing to safer and more efficient traffic management. Moving on to the extension, to make the system even more efficient, we have enhanced The LSTM model performance. We have enhanced the LSTM model by adding the gated recurrent unit. So here we have added the gated recurrent unit layer. These GRUs are simpler than LSTMs but still powerful, and they can help improve the speed and also accuracy of the predictions. This is especially important when we are working with the large data sets like traffic management system. By using GRUs, the model can process data faster without sacrificing the performance. Furthermore, here we have developed frontend using Flask framework. This will allow users to interact with the system for testing purpose, and it is integrated with the user authentication, which will ensure that only authorized individuals can access it. Moving on, moving on to the implementation. To implement this project, we have followed the steps which are mentioned in the flow of work. So let's discuss what are these steps. First step involves importing the necessary libraries and also the packages. So here we have imported Librosa for audio processing, Flask for web framework, and other machine learning libraries for model training that are Pandas, NumPy, Scikit-learn, and Keras. Coming to the next step, that is exploring the data set. Here, the data set consists of two main classes. One is road sound and the other one is siren sound. The goal is to classify audio files into these categories based on their sounds. So we will understand what is the structure of this data set. After that, the next steps comes in is the data processing. So here the audio files, that is the audio data, is shuffled randomly to ensure a balanced distribution of both the classes. This helps the model to learn better and avoid bias during training. Then comes the splitting the dataset part. Here, dataset is divided into two parts. One is training and the other one is testing. Coming to training data, we have 70% of the dataset in the training set and 30% in the testing set. Here, training set is used to teach the model and testing set is to evaluate the performance on unseen data. Then comes the feature extraction. So here in the feature extraction, key acoustic features such as MFCC, that we call as Mel frequency septal coefficients, Mel spectrogram, RMSE, that is root mean square error, and spectral contrast are extracted using the Librosa library. These features help the model to distinguish between road sounds and also the siren sounds. Then comes the model training part. Here, the extracted features are used to train the machine learning model. The model learns to classify the audio files based on patterns in the features. Then comes the performance evaluation. After training the model, its performance is evaluated using the test dataset and also the metrics called accuracy, precision, recall that are used to assess how well the model classifies the sounds. And now comes the part of frontend. A web-based frontend is developed using Flask framework. This includes setting up user registration and login functionalities with the support of an SQLite database for storing the user data. Then comes the front-end input part. So here the user uploads audio files through the front-end interface. These files are used for the prediction purpose. After that, the given audio file will be pre-processed at the backend. So the input audio files are pre-processed, which includes extracting the same features used during the model training, making them ready for prediction step. And that audio file is fed to the train model. So the train model is used to classify the pre-processed audio files, determining whether they are road sound or a siren sound. Finally, once the prediction is made, the result is displayed to the user on the front end, showing whether the audio matches a road sound or a siren sound. Moving on to the algorithms used, as we have mentioned in the proposed system, this is the proposed model that is used for classifying the road sound or a siren sound. And this is used for comparison purpose. And this is the extension model that is combining LSTM model with the GRU. So here in this model, we have combined this XGBoost model, multi-layer perceptron and deep neural network along with the LSTM. So multi-layer perceptron, deep neural network are the base models and the LSTM is the meta model in that model. And coming to the extension part, here we have added stacked LSTM with the GRU, that is gated recurrent unit. Moving on to the requirements, to implement this project, we need basic requirements which are hardware and software. Coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and hard disk of 25 GB. And coming to software, we need application of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let us execute. For that, we are supposed to open the code folder which contains source code files. So let us open the code folder of the project. These are the source code files in the code folder of the project. Let us understand each of them. How will they be used in the project? Let us open the dataset folder. So here we have two subfolders. One is road sound and the other one is siren sound. Here we have 200 samples of road sound and 200 samples of siren sound. So these we will be clubbing together and then we will train the model for classifying the both sounds. And in this model folder, we have the algorithm information that will be loaded into the project code during runtime of the application. And that algorithm information is stored in numpy files, .h5 files, pickle files, and etc. And this is also one model file. Coming to the static folder, this folder consists of files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal of the project. Then comes the templates folder. Here in this folder, we have files containing HTML pages that are typically index.html, about.html, etc., which represent different pages of the website. And in this folder, we have test cases that we will be using in the front end. So these are the total 8 different audio files that we will be using in front end. And coming to this app.py file, this .py file contains the information related to front-end logic of the project. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is the notebook.ipynb file. This is a Jupyter notebook file, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And the last one we have is the signup.db file. This file is a database file which is used to store the user information. So we have understood all the information about the code folder, source code files. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. So I'm copying it. Now open command prompt. Here it has been opened. Give the command cd, give the space and paste the path which we have copied now. Now click on enter. Here if you observe, current directory is changed to the code folder's path. Now we are supposed to compile the app.py file, that is the front end file. Give the command python space app.py and click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and port. So localhost is 127.0.01 and 5000 is the port unless configured differently. Now we have to copy this local link provided by the Flask framework. So copy the local link, paste it into any web browser. I prefer Chrome, so I will paste it in that. Paste the link and click on enter. This is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to sign up first. Click on sign up and enter all the registration details if you are registering newly. I have already registered, so I will directly log in. Click on login. Give your username and the password and click on login. We have logged in successfully and we are redirected to prediction page of the project. So here you can see a choose file button, right? We need to click on that for uploading the audio file. So click on that. So these are the test cases that we are going to upload. So these are the audio files that we will be uploading for predicting whether it is a siren sound or a road traffic sound. Before that, let's listen to these audios. Let's open the code folder. It is in this folder, right? So let's open this folder. So first, let's listen to the class 0, zero file name and see what type of sound that audio file has. So you can listen a siren sound, right? Let's upload same audio file and see what will the application predict. Click on upload. So this given audio file will be pre-processed at the backend and then it will be fed to the trained model and that will be giving us a prediction. So here we got the prediction. So the given audio file is classified as the siren sound. So here if you observe, it is classifying correctly. Now let's check with the other audio. Let's check with this one. So you can hear a road sound, right? So let's upload that file. Let's click on choose file. Let's upload the file name 1, that is the audio file 1. Click on upload. And here you got the prediction that audio is classified as road sound. So here also it is classifying correctly. Now let's listen to some more audios and then upload it for prediction purpose. So let's listen to the audio 7. So you heard a traffic sound, right? That is a road sound, right? Let's close this and upload the 7th file. Click on prediction. Click on choose file. Upload it. Click on upload. So here you got the correct prediction, that is road sound has been classified. So by the given sound, the application is classifying that road sound. Let's try with one more case. Let's try with this one. So you heard siren sound, right? Let's upload this file name 6. Click on choose file. We will upload this one as we heard it just now. Click on upload. Here we got the prediction that given audio file is classified as a siren sound. In this way, if you upload all the test cases, you will observe the prediction that is correctly classifying the sound of that particular audio. If it is siren sound, it will classify as siren sound, or if it is road sound, it will classify as road sound. Now let's check with the graphs. Click on graph. Here we have the graph. So this is the confusion matrix of the stacked LSTM with GRU graph. So this is the confusion matrix. And this is the extension stacked LSTM with GRU models, ROC, AUC curve graph. Here on x-axis we have false positive rate and on y-axis we have true positive rate. And in this confusion matrix on x-axis we have predictions made and on y-axis we have actual values. This yellow color diagonal represents the actual predictions and this purple color diagonal represents misclassifications. And here if you observe with this extension model we have 0 misclassifications and complete correct predictions. True classifications, these are the true predictions and these are the misclassifications. Moving on to the accuracy score. This is the accuracy score comparison graph. Here on x-axis we have accuracy score and on y-axis we have all the algorithms which are trained on the dataset for classifying the sounds, whether it is siren or road sound. And this is the precision score comparison graph. This is the recall score comparison graph. And here we have FN score comparison graph. So these are the metrics, that is accuracy, precision, recall and FN score are the metrics used to evaluate the models, that is the classification models. Now click on sign out. So by the switch is by uploading the audio files, it will classify whether it is a siren sound or a road sound. This will help the ambulances and any required, that is emergency vehicles, to save the lives. This is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.